So, let us see how to go about it. Say, let us consider an example. Find the absolute extreme values of f of x equal to x to the power 2 by 3, and where our function is defined only on minus 2 to 3. Though this function can be defined elsewhere, but our search is limited, function is defined on this interval only, minus 2 to 3. And how does it act? F of x is x to the power 2 by 3. Now, how to get its maximum or minimum values? All that we have to do is, first the end points are possible points minus 2 and 3. Then we will go for the critical points. So, all those critical points and along with these end points are possible values where its extreme values can occur. So, let us find the critical values first. So, if x equal to 0, then it can be 0, but what about differentiation? Well, if you take derivative of f x, it is 2 by 3 x to the power minus 1 by 3. So, this is not defined at 0. So, at 0 we do not define it is not differentiable, right. But if x is non-zero, then its derivative is 2 by 3 x to the power minus 1 by 3, and if we substitute x non-zero, f prime x is also not equal to 0. So, that means possibility of critical point is 0 only, where it is not differentiable, okay. And there is no other point. There are points where it is differentiable, but all those points are not critical points because f prime does not vanish there. So, no other critical points, 0 is the only critical point. So, we have now three things. You have 0, possible extreme points are end points minus 2 and 3, and the only critical point 0. Then all that we have to do is compare the values and find out which are the extremum and maximum or minimum. So, f of minus 2 we find it is 4 to the power 1 by 3 from here, and f of 0 is 0 of course, and f of 3 is 3 to the power 2 by 3, which is 9 to the power 1 by 3. Now, out of this we find that maximum is 9 to the power 1 by 3 at 3, and minimum value is 0, right. So, that is also critical point. Minimum is achieved at 0, maximum is achieved at 3. So, point of absolute maximum is 3, point of absolute minimum is 0, and the absolute maximum value is 9 to the power 1 by 3, and absolute minimum value is f of 0, which is 0. That is what we conclude from this. Let us take another similar problem. Suppose you have f x equal to x to the power 1 by 3, again defined on the same interval, closed interval minus 2 to 3. So, let us find out derivative and see the critical points. So, it is not differentiable at x equal to 0, and x non-zero it is differentiable, and its derivative is 1 by 3 x to the power minus 2 by 3, but they never be equal to 0 if x is non-zero. So, they are not critical points, okay. So, the only critical point again is 0, and we have the end points which are minus 2 and 3. So, we compare the values. F of minus 2 is 2 to the power minus 2 to the power 1 by 3, f of 0 is 0, f of 3 is 3 to the power 1 by 3. Again you get the maximum value as 3 to the power 1 by 3, which occurs at 3. So, we say that the maximum value of f x is 3 to the power 1 by 3, and the point of absolute maximum is 3. And again here f 0 is not minimum because there is a negative value. So, minus 2 is a point of absolute minimum, and the absolute minimum value is minus 2 to the power 1 by 3. There is no b here. So, the absolute minimum value is minus 2 to the power 1 by 3, and it occurs at x equal to minus 2. Okay. So, we will take some more examples. Let us say the function is given as f of x equal to x to the power 2 by 3 into x plus 2. What is the domain? It is defined everywhere of course, right. 2 by 3 is there. So, we have to find its local maximum and local minimum. So, that means they will occur at critical points. There is no end point here, right, is domain is whole of R. So, all are interior points. Now, we find the derivative. So, derivative is x to the power 2 by 3 into x plus 2, it is f into g for product of two functions. So, first we take f times derivative of g, f g prime. So, which is f is x to the power 2 by 3, g prime is x plus 2, derivative is 1. Next, derivative of x to the power 2 by 3, which is 2 by 3, x to the power 2 by 3 minus 1, which is minus 1 by 3, and g, which is x plus 2. So, you simplify, that gives to 5 x plus 4 divided by 3 into x to the power 1 by 3. So, to find the critical points, we should see where this becomes 0. So, it is 0 at this point, x equal to minus 4 by 5 from this numerator. And what about where else there can be critical points? The points wherever it is not differentiable. So, x to the minus 1 by 3 coming, that should signal. So, we will find that it is not differentiable at x equal to 0. Now, we have two critical points, right. One is where it is differentiable and derivative 0, another where it is not differentiable. So, out of these 2 points, we should find out, decide about the maximum and minimum. Okay. So, how do we go about it? If you go for absolute maximum or absolute minimum, you just substitute x equal to minus 4 by 5, find out f of minus 4 by 5, f of 0 is 0 of course, and whichever is larger that will be maximum, whichever is smaller that will be absolute minimum. But we want local maximum and local minimum. So, that means in the neighborhoods, some neighborhoods of minus 4 by 5 and neighborhoods of 0 we have to compare. So, let us take at 0 first, that will be easier. So, let us take some neighborhood, it may be say minus 1 less than x less than 0, you could have taken minus half also, but bigger might give a trouble. So, smaller is better to find out some neighborhood. So, in this neighborhood minus 1 less than x less than 0, f of x it is negative, right, x is negative. So, this becomes negative, you get f of x and this becomes positive now, it is 2 minus 1. So, you get f x is greater than 0, which is f of 0, right. Is that okay? X is 0. So, you are taking the left neighborhood and f of x is bigger than 0, that is what you see from the graph also. Now, you take a right neighborhood, there also you find that f is bigger than 0, bigger than f of 0. So, at 0 there is a minimum, right. So, critical point x equal to 0 is a local minimum point, where the local minimum value of f x is 0. Now, this kind of analysis will be difficult for x equal to minus 4 by 5, right. So, that may come somewhere here, minus 4 by 5, somewhere there, because the function is complicated, but still it can be done by computing the inequalities. However, from the graph also you can see directly that x equal to minus 4 by 5 is a point of local maximum. You have to really do this kind of thing, take a neighborhood around minus 4 by 5, so you limit to 1, so that it will be easier to compute this one and it will carry through. Okay. Fine. So, let us take another example. Say f of x equal to a x cubed plus b x square plus c x plus d. It is a polynomial of degree 3, a cubic. So, we are not going to find the critical points or extreme points, but something else it is asking. It is telling how many critical points and how many extreme points of f x can have. So, how do we proceed? To find the critical points, this is a polynomial, it is differentiable everywhere, right, and it is defined over whole of R. So, every point is an interior point, but f prime of c will be quadratic. right, this 3 x square into a plus 2 x into b plus c. So, that can vanish at most at 2 points. If there are real roots, there will be exactly 2, if not there will be 0, right. There will be complex roots only 2, so it will be 0 depending on ABCD. So, that is what we are going to do. We say f prime x equal to 3 x square plus 2 b x plus c, it can have at most 2 real roots. So, since there are only 2 real roots maximum, it can have say 0 or 1 or 2 critical points, a maximum of 2 critical points. That is what it says, right. Okay, let us see how to proceed. Suppose I take the polynomial x cubed plus x, my a is 1, b is 0, d is 0, c is 1. So, f x equal to x cubed plus x. Now, does it have any critical point? We get the derivative as 3 x square plus 1. So, this is never equal to 0 for any real number. So, it does not have a critical point, right. And also x cubed plus x, if you look at the graph, it is growing and x will be added to it. So, you will see that there is no extreme point, neither negative nor positive. It grows to infinity and down also it decreases to minus infinity. It will neither have extreme points, maximum points nor minimum points, and it has no critical points. So, that serves an example for the 0 case. Now, let us take f x equal to x cubed minus 1. Its derivative is 3 x square equal to, so you want critical points, equate that to 0, we get x equal to 0. So, 0 is a critical point, right, but it is x cubed minus 1, again it is growing with minus 1 shifted. So, it has also no extreme point, right, but it has one critical point. If you take x cubed minus 3 x, okay, another example, then where are the critical points? You differentiate, it gives 3 x square minus 3, and if you equate that to 0, you would get x equal to plus or minus 1. These are the critical points. So, there are 2 critical points, first one 0 critical point, next 1 critical point, next 2 critical points, and here both are extreme points. Okay, that is clear from x cubed minus 3 x, both are really extreme points. You have to find the some neighborhoods and then complete the argument, but that is what you see intuitively, x cubed minus 3 x. So, it will have one extreme point plus 1 will be say 1, if you substitute it gives 1 minus 3 which is minus 2, that is at f of 1, and f of minus 1 that is equal to minus 1 minus plus 3 which is 2. There is a maximum value at minus 1 and a minimum value at 1. Okay. So, all sort of things could happen, that is what we see from this for a cubic. Okay. But it can have either no extreme points, or we have shown an example where it will have 2 extreme points. We will see later why only one does not happen, right. It either has no extreme points, here you see 2 examples, no extreme points, and or 2 extreme points, the last one. Critical point is 1 in the middle for f x equal to x cubed minus 1, but it has no extreme point. So, we will later see why such a thing is happening, that there is one extreme point, that case is not possible for a cubic. Okay. So, of course, from its graph you can see in general the graph would be something like this, and that should give the answer. Okay. But we will see why this happens analytically. So, let us take another example where it is a different kind of thing. It is given that f of x is an even function, and also this has a local maximum at x equal to c. Okay. We want to find out whether there is a local maximum or a local minimum or some such thing happens at x equal to minus c. Because it is even, that is why something to do with c and minus c. So, what do we do? In fact, if you take f of c, that is equal to f of minus c, because it is even. So, what can you say about x equal to minus c? If it is absolute maximum, then of course, you could have told directly there is absolute maximum at x equal to minus c, because it is that value, but it is only asking local maximum at x equal to c. So, since it is local maximum at x equal to c, we have a neighborhood of c, say c minus delta to c plus delta, where if x belongs to that neighborhood, then f of x is less than or equal to f of c. That is what it says. Now, what will happen in a neighborhood of minus c? Well, since f is even, f of minus x equal to f of x and f of minus c equal to f of c. Okay. So, we conclude that f of minus x is less than or equal to f of minus c, for which x, whenever x belongs to c minus delta to c plus delta. So, in that case, minus x belongs to what? If x belongs to c minus delta to c plus delta, then minus x will belong to minus c minus delta to minus c plus delta, minus of this and minus of this, but reversed. So, minus x belongs to this, right. So, since minus x belongs to this, we have a neighborhood of minus c, where if this is a t, t belongs to that neighborhood, then f of t is less than or equal to f of minus c. So, f of minus c is also a local maximum, right. F of minus c is also a local maximum value. So, where does it occur? At x equal to minus c. So, you would say that there is a local maximum of f, or f has a local maximum at x equal to minus c also. Is that fine? Okay, so, let us solve some more problems and see how this idea was exploited. So, we are required to find the absolute maximum, absolute minimum and the points where this absolute maximum, absolute minimum occur for the function f of x equal to 4 minus x square square root, where x belongs to minus 2 to 1. So, all that we have to do, find the critical points and so on and the end points. Now, differentiate, that gives 4 minus x to the power half, right. So, it will be half derivative with respect to 4 minus x square. So, here 4 minus x square, then 4 minus x square derivative with respect to x. So, that gives minus 2x. So, 2 cancels, that is minus x divided by square root of 4 minus x square, and this is equal to 0 when x equal to 0. Therefore, the only critical point is 0. 0 is an interior point, of course. So, we have now 3 points, plus or minus minus 2 and 0. So, where it is not differentiable, they are also critical points, right. So, you have to see where it is not differentiable. It is not differentiable at minus 2. Okay. Anyway, 2 is not in the domain. So, minus 2, but minus 2 is an endpoint, anyway we are going to consider it. Okay. So, we just evaluate at minus 2, 0 and 1. We find that f of minus 2 is 0, f of 0 is 2 and f of 1 is root 3. So, it has a maximum value 2 at x equal to 0 and it has a minimum value 0 at x equal to minus 2. So, it is fairly straightforward. So, maybe one more exercise. So, find the absolute maximum, absolute minimum and the points where they occur for the function f x equal to sin x, where x is given from the closed interval minus pi by 2 to 5 pi by 6. Again we differentiate. So, we get f prime x equal to cosine x and we equate that to 0 to get the critical points. Of course, it is differentiable everywhere. So, we do not have to worry in the interior. So, this f prime x equal to cos x, this is equal to 0, where it is a multiple of pi by 2. So, at minus pi by 2 and also pi by 2, right, but minus pi by 2 is an end point. So, interior point is pi by 2. So, the only critical point is x equal to pi by 2. Then we have two more points, the end points. There we have to compare all the values. So, sine of minus pi by 2 which is minus 1, sine of 5 pi by 6 which is half, and sine at the critical point pi by 2 is 1. So, out of this maximum is here at pi by 2 and minimum is at minus pi by 2 which is minus 1. That is what it says. Fine. Let us go to next problem. So, find the extreme values of the function f of x equal to square root of 3 plus 2x minus x square, and also the points, extreme points, right, points of the extreme values of function f of x. All these things we have to find. So, again we proceed the same way. So, now you see it is we are not given with the domain. So, what is the domain? It is square root. So, 3 plus 2x minus x square must be greater than or equal to 0. So, if you factorize that, that gives 3 minus x into x plus 1. So, it is greater than or equal to 0. That means, x must lie between minus 1 to 3, minus 1 and 3. It is x plus 1 into x minus 3 less than or equal to 0. So, if it is inside minus 1 to 3, then that x minus 1 which is x plus 1 and x minus 3 that is less than or equal to 0. So, that gives x belongs to minus 1 to 3. So, that is our domain now. We know that it is minus 1 to 3. Then there we consider the interior points and then critical points and then the end points and compare. That is what we do. So, when you differentiate, you get f prime equal to 1 minus x divided by 3 plus 2x minus x square, and this is 0 when x equal to 1. But x equal to 1 does not belong to our domain, right. Is that fine? No, it is minus 1 to 3. So, we have minus 1 to 3 and x equal to 1 belongs to the domain, and that is an interior point of course. So, that is the only critical point, right. X equal to 1 is the only critical point. Then we compare just at all these points f of minus 1, f of 1 and f of 3, and find that the maximum occurs at 4, maximum value is 4 occurring at 1, and minimum value is now occurring at 2 points, one at minus 1 at 3. So, minimum value of the function is 0 and the points of absolute minima are now 2, minus 1 and also 3, right. These are the endpoints. So, let us stop here.